Good afternoon, everyone. This is Bootcamp number 3. My name is Laura Precupanu. I'm a senior expert capability excellence working for OMV Petrom. I'm one of the organizers of the SPE Europe Energy Geo Hackathon, and today I'm going to be your moderator. As part of our session, you know pretty well the format, so we have one speaker for the entire session. Today is József, and I will introduce him in a few minutes. As part of our sponsorship opportunities, when we invited our sponsors to be part and support us with this hackathon, we offered them a sponsor benefit, also a small presentation before one of our bootcamps. So for today, we have with us Boris Vidos, who works for INA-GEO, and Boris will present shortly his company, what are they doing, and what he is doing for them. So Boris, the floor is yours, and please go ahead.
Laura, thank you very much. Let me just share my screen, please. Just please let me know what full screen.
We can see your
think
screen.
now. Okay. So hi everyone. I'm really glad to be here today. I am today presenting shortly the company of Energia Naturalis, actually ENA-GEO, which is specialized for works related to geothermal energy. I'm also glad that I can say that my company is a sponsor for Geo Hackathon, and that also I am a part of organizing board of Geo Hackathon. So without further ado, I would just like to go through a few slides and to explain what ENA-GEO is working right now, and where we are in Croatia in geothermal sector. So here you can see a thermal map of Croatia, where Croatia has a really huge geothermal potential. So at around 2000 meter depth, we have around 100 degrees Celsius, where these temperatures can go even higher than 150 degrees Celsius over 3000 meters. Currently, Croatian Hydrocarbon Agency, which is also in chief for geothermal purposes and energy also, estimated the total capacity of electric megawatts to 500 megawatts. In total, if we go to count also thermal and agriculture possibilities, we can even go over a gigawatt. So this is the current assumption. Today, there is more than 30 active geothermal projects in Croatia. And actually, 3 or 4 days ago, they just published 6 new tenders that are awarded to some new companies that joined in Croatian market. ENA-GEO is member of Energia Naturalis ENA Group, which is a holding of groups that works in different aspects of energy sector, from PPD that was specified for natural gas, to Energia Naturalis that has ENA-Logic, ENA Solar, ENA-GEO companies, ENA Transport. Also, they have a big share in Rijeka, Ploče and Port Rijeka. Geothermal energy in Croatia is currently developing mostly around electricity production, while ENA is also aiming to utilize district heating and agriculture opportunities, as Energia Naturalis also has its own company for production of vegetables and fruit. So in the few years in front of us, we hope to have the full cycle closed in our projects. In general, ENA made 2 big acquisitions in 2022. So they bought 2 companies which are holders of 2 geothermal projects in Croatia: Geopower Zagoča, this is a company that I'm currently working in, and Geopower Babina Greda. Geopower Zagoča is the first geothermal water exploration field awarded in the Slatina 2 area. In the fall of 2022, we had a workover on PS5 well, which was deep well drilled to 5,100 meters in 1985 in search for hydrocarbons. Unfortunately, the well was, or fortunately for us, well was not they didn't find hydrocarbons then, but they found deep and hot geothermal aquifer at the depth of 5,050 meters. So unfortunately, this well was too old and we couldn't use it for current production of geothermal water. So now we are starting a new drilling campaign, which should start in April or May 2024. And we plan to drill 4 deep geothermal wells, roughly 5 to 5,400 meters vertical depth. Geothermal power plant Zagocha that we plan to build in the first phase would be almost 20 megawatts electric, with potential of expansion for additional 20 megawatts, depending on our first wells results. This is our actually currently the most advanced project, and we hope to start drilling next year. GeoPower Babina Greda is a bit behind the GeoPower Zagocha project, but still in 3 or 4 years to finish if everything will go upon plan. In March 2023, we had the HDM measurements in the field. Measurements showed the good temperature on a lower reservoir, and we have a deeper reservoir which is roughly 4,500 meters deep, but we don't have the access to this reservoir, so we have to drill new wells because the old well only touched the shallower part of the reservoir. So now we are also planning drilling campaign, but unfortunately we need some more time for documentation, as this documentation and regulation stuff in Croatia tend to take their toll, with time. But still, it's achievable maybe in 1.5 years to get all of the permissions and documents to start drilling. Our plan for Babina Greda is to build 15 megawatt electric power plant, with also potential of expansion for an additional 20 megawatt. So these are 2 currently operating projects. We are working on both of them, and Anna is also interested in other projects in Croatia and in region. I didn't want to take any more long discussions or something. For the end, I want to thank you for your attention, and I want to leave my email address here. For all of you that will be interested or will have some questions, you can send me an email and ask whatever you are interested in. I would like to thank once more Laura and Gabi for having us here. And if this is it, I can stop sharing my screen now.
Thank you very much, Boris. And thank you, INAGEO, for your help. It's really very much appreciated. Please convey this message to you, the upper management, and thank you for everything you are doing for DSP. And with this, I think we can jump directly in what is our today's session. Please allow me to share my screen. Just a second. Do you see my screen?
Yes, we can see the screen.
Okay, thank you very much. So this is the overview of our bootcamps. So we had already 2 sessions. Today is session number 3, and this is the schedule until November 1st. And for today, we have seismic data processing. And it is with great pleasure for me to introduce my colleague, in fact, József Orosz. He works for OMV Petrom. He is the department manager for seismic shared services. Prior to his work with us in OMV Petrom, he worked at group level in OMV in Austria as department manager for seismic data processing. He held also various positions, from project leader to technology center manager in multiple countries, including Kazakhstan, Angola, Oman, UAE, Saudi Arabia, and the Netherlands. He finished his studies at the University of Miskolc in Hungary. And without any further ado, József, welcome. Thank you for accepting to be with us today. Thank you for your enthusiasm when we mentioned the SP Europe Geo Hackathon, and the floor is yours.
Thank you very much, Laura. Yes.
I just wanted to add one more thing that I know from you, that your session will last between 60 and 70 minutes. And for our participants here in the call, any questions you have for József, you can type them in the chat box, and we will address them one by one at the end of the session. József, please go ahead.
Thank you very much for the introduction, Laura, and welcome everybody. I got a very hard task to introduce to you very fast the seismic data processing and imaging, which is quite big topic, and I tried to scale down really for this almost 1 hour presentation. I hope things will be clear, because almost each topic can be a very long conversation, what you will hear today. So I just jump through my CV and starting with the agenda. So I will use a small introduction about the basics of the geophysical data, because several of my so the 2 previous presentations showed something, but I think it's good to just have a look again. And then I will go through in more details the pre-processing sequence in several steps what we have. And then at the end, I will finish with the migration, with the time and the depth migration, how we can generate at the end the subsurface image. So let's start. So introduction. So first is the P and the S wave, what you already, I think, saw this picture. So first we are discussing about the P wave, which is the primary waves and also referred as compressional and longitudinal wave. And a P waves has a higher velocities than the S waves. P waves are the predominant waves used in seismic exploration. So everything what we are discussing after is P wave. And then also what we have to know, just as a side note, that we have a special vertical component geophones what we are measuring this, or receivers when we are measuring this P wave on the field. Yeah, the other big wave family is the S wave, which is the secondary waves, also refers to as shear or transfer wave. They have a transverse particle motion, and velocity is lower than the P wave velocity. Also, they cannot propagate in fluids and gas. And shears could be a vertical and horizontal component. And usually we have multi-component to really measure this wave, horizontal component, but the multi-component give us a full view. So this is the waves, which is at the moment we're just touching in noise session, because also the S wave is connected with the ground roll, which is a quite strong noise in the processing, but we are concentrating mainly on the P wave component. Another law what we have to also introduce, this is how the waves are bouncing back with different surface and reflector. So what you have to see here, you are seeing 2 layers, a very simplistic model. The upper layer has V1 velocity and ρ1 density. The lower layer has V2 velocity and ρ2 density. Then we have an incident energy. And when the horizontal, the layer, when it's reaching the horizontal layer, is bouncing back. And this is what we call as a reflected energy from the reflector. And then we have one part of the energy which is going forward, and this is the transmitted energy. So the base rule is that the angle of incidence is A, and this is the same as the angle of reflection, which is B. And also the C is depends. The C angle is depends on the velocities and the velocities in the layers. And this is what the Snell law is writing down quite nicely. In this case, how the reflection and the transmission is happening in these 2 layers. There is another layer with the refraction, but at the moment I am not talking about, because then it will be too much information, and it's for this presentation it's a small part for the presentation. Then, so we have the Snell's law, how we are observing the waves. So how is generated this waves, P waves, which is going through on the Earth. So this is the Earth convolutional model. We have a geologic model on the left side. We have 5 interfaces which is going through. You can see on the left side the different velocity from 2000 meter per second to 4200 meter per second. And all of this layer boundary at the moment is generating for us air function. This is the reflectivity series. So here in this part, you can see horizontally the time axis, and the size of the arrow and the direction is the reflectivity series. Depends if you have inversion or not, but this reflectivity series is representing the boundaries for each geological layer. Then when we are emitting a source to the Earth, we are getting a source function. This is a wavelet which is generalized. It could be a vibrator wavelet, it could be dynamite or air gun. And this wavelet is convolved one by one for each reflectivity boundary and with the reflectivity series. So you can see that as we have these 5 layers, we have for each reflection is contributing to the final seismic wave. And then we are adding together this 5 reflection. And this is at the end, which is representing for us the seismic wave, which is the combined reflection time series. So when we are building up the equation for this effect, then the seismic trace in theoretically, which is S, is obtained by the convolution of the reflection coefficient time series with the wavelet. So this is what you can see in the bottom, that the seismic wave is equal the reflection coefficient convolved by the wavelet. So this is how we are starting to see a wave which is spreading in the deep. And then just to show you how it's happening. So again, we have a horizontal reflector with 2 layers, Z1 and Z2 layers, and we have a source in the middle, and then the receivers is spread at the 2 sides of source location. So if we start to the shooting, then you can start to see how it's going down in the waves, and then is bouncing back one part of the energy, and the other part of the energy is transmitting in the second layer. So this is what we can define at the end, that we have the incident wave, which you can see on the left and the right of the snapshot what we did from this waves, and then we have the reflection wave which is coming back from the first boundary, and then you have a transmitted or refracted wave which is going into the second layer, and it's continuing the traveling to the deep of the Earth. So again, just to play again with this thing, so that it's coming the incident energy, then reflecting back one part, and one part is emitting to the second layer. Yeah. When we have the source location and the receivers on the surface, the next page I am showing you what we are measuring on this exercise. So again, you can see in the top the receivers and the source location. The vertical axis at the moment is the time, and the P direct arrival, you can see this is the first break, which is arriving first always for each shot, and the reflection is appearing from the first boundary, which is reflecting then from that layer. Yeah. So this is how we are generated the waves and what we are recording usually on the surface. So unfortunately, we have some unwanted effects also in the seismic. So you can see the previous example before with some geology in the deep. And we have a vibro-sized truck as a source. Then we have the geophones, and we have the instrument which is recording the event. And then we have the target reservoir. So what you will see again from the vibrator coming the wave, and then is bouncing back from each layer, and then at the end what we are recording, this is the seismic record. We have some unwanted effect, unfortunately, what we have to also deal during the processing. So one part is the air blast, when we are shooting that the air blast is going through on above the surface, but as the geophones are sensitive to this, it's recorded. Then we have the ground roll, which is just going through in the upper part of the near surface, and this is also recorded by the geophones. I will show you how does it look like on the seismic record. And of course, we have multipulse, and also I will have a short section about the multipulse just to show the effect and how we can recognize them. So this is the seismic experience, and of course we have the topography, because at the moment, as I understood, your data is connected with onshore, and that's mean that you have issues with the topography when you start to see the data. Yes, so all of these things, at the end, if I am putting a theoretical shot points with several layers, and again we are shooting and is bouncing back for all of the layers, the ray path, then we can build up a section which looks like below the surface positions. And then what we can see that this section is very nice and clear, and finally we can just have to turn to the final image, remove some effect, and we are fine. The issue is usually that most of the time, and this is what you will see on the examples, this is not that clear. So this is a fully recorded shot point with different noise included. And you can see, but for example, if I am putting the one refractor on the left side on the clean shot gather, we can see quite nicely the position. But if I'm going to the right side, to the real recorded shot point, what we can see that finally in one part is visible, one part is not visible, but definitely there are lots of noise which is included in this recorded shot point. And also, of course, we have several other noise. So we have a background noise like ambient noise. If you are doing the measurement like a road, a train or something, then we have, or the city, it has a high ambient noise. So this can generate some issue and we have to attenuate them. Then we have the first refraction, which is going through the first part. This is also valuable part of the signal as we can use for static correction, what I explain later. Then we have the reflection, what we would like to preserve. And of course, we have the ground roll and the airwave noise, which is this triangle in the middle, and it can show how it's affecting really the quality of the current data. So then I'm changing about the seismic data processing. So what is the seismic data processing? I'm using here a small definition which was created by Sharif, who is one of the main guru in the processing. So the seismic data processing is to change the data, usually to improve the signal to noise ratio to facilitate interpretation. Processing operations include applying corrections for non-perturbing causes, rearranging the data, filtering it according to some criteria, combining data elements, transforming, migrating, measuring attributes, display, etc. So it's lots of things what we are doing, lots of data manipulation, but at the end, our goal or main goal to what we would like to reach with the seismic data processing: first, to improve the resolution. Second, to improve signal to noise ratio. Third, obtain an accurate reflection time and position. And also we would like to keep amplitude fidelity as much as possible. So all of these things is altogether is the same importance. And based on the task and the data quality, some of them can be more important than the others, but usually this is our main goal during the seismic data processing sequence. So I am changing now, and I put here a very simplistic processing flow, which I would like to go through one by one and show some example about and give some explanation. So the different steps, it can be mixed. So this is a very basic flow, but the steps can be mixed, can be iterative. Some step can come back later when we have different data position, like noise attenuation, static correction, NMO correction. All of them we can do several steps. For example, update the velocity model, see how we can change the signal to noise ratio. But as a simplistic processing route, I describe these things. So we are starting with reformatting, geometry, amplitude recovery, then noise attenuation, filters, deconvolution, common midpoint gather sorting, static correction. This is valid mainly for land, but also some part can valid for marine. Dynamic correction, as also you can hear sometimes NMO or normal move out corrections and mutes, stack, and at the end the migration. And also I put another part, the multiple attenuation, because also this can create some additional coherent noise where we would like to attenuate properly from our data. So let's start the reformatting, geometry, and amplitude recovery. These are very, very easy and very simple step, but we have to put always in our mind that the data has to be the right geometric assignment. If it's not measured well, or we are not assigning the data with the proper geometry, then our data almost useless and our result is useless. So we have to reformat first an international exchange format. Usually you will see SEGD or SEGY format to an in-house format for the processing company. This is the first step. And the second step, we are assigning the geometry to this format. For the recent data, this format is already included in the SEGY or the SEGD data. In the earlier time, we are getting usually a support navigation files, and this we are assigning separately for the data after reformatting. It's again very important to properly QC and check these things, because from the first step we can do a big mistake, and it's very important that we are doing this. I had some example about possible geometry errors, but it's lots of time to explain properly these things, so I excluded at the moment this presentation. If you have some further interest, I'm happy to answer, to show some example later on. Pre-processing, so we have the amplitude recovery. This is when we are shooting on the surface. At the moment, the amplitude started to be decreased, and this is going through a spherical divergence, and this correction we are calling the spherical divergence correction as the wave propagates away from the source. And most of the time we can use the equation, the 1 per radius of the Hall sphere to recover this energy loss. So what you can see here, you have the shot point, you have the distance, radius of the Hall sphere as it's going down. And I have an example, how does it look like, the amplitude recovery. So left side, we have the shot gather before the amplitude recovery, and in the left and right, you can see the offset, how it's changing, and vertically the time. And you can identify that how it start to be weaker and weaker, the signal or the noise, both of them together, when it started to be going deeper and also far in offsets. But then when we recovered properly the spherical divergence, then we can see that areas where it's almost no information, finally we recovered very nicely the data, and we have the balanced shot point. This is the first step what we usually applying on the data sets. So yes, then the next step is the noise attenuation in the filters. So here first, what is the main objective when we are doing the attenuation, the noise? So without noise attenuation, signal may be distorted, signal may be also masked, so we don't recognize at all where the signal is. And noise, if we are keeping there, may be spread across datasets if using multi-channel processes. So for example, migration is a multi-channel process, so if you have a strong noise, also this can be spread to several traces, and then is really destroying the picture. As a basic, the definition, the signal, that part of the data which is required. So normal is primary reflection information or diffraction before migration, and the noise is everything else. So what we are seeing many times, really lots of noise, and this is what I will show you in the next pictures. The noise can be random or can be coherent, so both of them is creating different challenges for us. So main steps for the noise attenuation: first, we have to recognize of the noise content of the data. Is it connected with the frequency? Is it connected with higher amplitude? Is it connected with linear noise? Is it connected with hyperbolic noise? Any kind of noise content. Then we have to find a domain where we can separate properly the noise and the signal. So this is what we have to see, and nowadays it's coming more and more that we are trying to model the noise in different domain, different part of the data, and then we try to really to attenuate on that part, which is the right domain for it, and then gain it back. And what is very important, we would like to attenuate the noise content without really touching the signal or distorting the signal. So as much as possible, we would like to do amplitude preserve processing. And for that reason, we have to take care how we can removing the noise. And we are putting several trials, iterative trials, to find the best way to attenuate one type of signal. I would like to show you a very small example that how the noise attenuation is working, and then some real example, of course. So as you see here, we have a small shot record. The horizontal axis is the offset, the vertical axis is the time. And then what we would like to do, we would like to preserve the signal, which is the A and B. And then we would like to remove the noise content, which is at the moment is linear noise mainly. And for that reason, we have to convert this data, what we call this frequency and wave number domain, is FK domain as we are calling. And then when we are transforming this to the FK domain, this small shot gather, then usually the signal is aligning on the vertical axis, and the noise, the linear noise, are aligning on the horizontal axis in this part. And as now we have a good separation between the signal and the noise, we can tell that, okay, we are removing the noise from this part, and then we are converting back with the reverse transformation to the TX domain, and then we are getting back the gathers without noise. So what you can see, the very strong linear noise, which is signed by X, almost completely removed from the sample gather. And also you can see the event is not too much affected, but definitely the B is revealed the real behavior of the event, and now we can tell that the gather is at least linear noise free. Yeah. So let's see what kind of noise can we have. We can have, as a noise example, noise generated in the fixed surface position. So this is usually it's a random type of noise, but what we can see that you can see here several shot gathers next to each other. I put an orange arrow that how the noise content, which is a stationary content, is connected with one location, is going through the spread as we are going ahead with the shot points. And we can recognize that really it's a very located area where we have this higher noise content. What we can tell, most likely this is a random noise, maybe, I don't know, it's an oil pump or a small factory in the middle of the spread, and usually this is generating for us noise what we have to remove because this is not connected with the acquisition. You can see the spherical divergence correction on the shot gather. So on the but the noise which is stationary, you can see almost from top to bottom the same energy. So that's mean really we can separate based on most likely frequencies and the amplitude differences. Then another noise example from the North Sea. You can see on the left side on the picture how does it look like the sea surface is very rough, lots of waves, and this lots of waves on the streamer is generating lots of noise. So this is what you can see as a vertical vertical lines these noises, and our goal to remove completely this noise as much as possible and improve the signal to noise ratio. Now I am changing to the land, and you can see here one shot gather. It's very similar what you see in the beginning when I showed the different possible noise content. And what we can see in the middle, we have the ground roll and also the airblast noise. And if you see on the left side, we have some higher energy 1-1 trace noise where maybe a receiver point is next to a power line or some road, and it starts to be higher energy, more noise on it. So our goal to review fully the shot without this kind of noise, and this is what you can see in the middle. So if we are removing all of the energy, guided wave, refracted wave, ground roll, air blast, different burst noise, at the end we are able to remove all of the noise, and we are revealing the gathers with the primary data. And then you can see on the right side of the difference, which is representing for us really lots of energy to remove. And what we have to take care during this removal, that we are not touching the primaries, and we are trying to preserve the amplitude as much as possible. Also, we don't want to lose any structural setup. So we have several methods to do this. On land, this is one of the most dangerous things, because sometimes the diffraction can be attenuated a lot, and also some reflection energy can go to the wrong place. How does it look like on the land section? So it's the same exercise, but now on stacks. So we stack together that data what we saw on the shot gathers. And the left side, you can see the stack before the noise attenuation. So, and the middle, you can see the stack after the noise attenuation. So after noise attenuation, you can see lots of event is appearing, which is on the left side. You cannot identify at all because the noise content is that high of the input data. And on the right side, you can see the difference. So again, here, what is the main challenge? We can attenuate the signal very well today, but always we have to take care not to attenuate the primaries during the noise attenuation steps. In this case, it's happened quite nicely. So if you see the difference, usually what we are looking for, that what is the primary content, what we have still in the difference, and we were not able to really recognize during this exercise. So this is, in this case, what we can tell, that the first noise attenuation steps were working quite nicely for this data set. Next step, so we created a very nice clean data, what you can see here in the middle. And then the next step to go further in the processing sequence, and we are reaching the deconvolution part. So the deconvolution part is what we would like to remove the seismic wavelet, which is the response of the filters in the seismic system, except the reflectivity. And also we are adding one more part for the seismic trace, and this is the noise. But it's a different kind of noise what we discussed before. So the whole seismic trace is building up the wavelet convolved with the reflectivity series plus the noise. And this is what you can see on the lower picture. And this is how the wavelet is building up. So how the noise is also, wavelet and the noise is building up for one trace. So the seismic trace is the output of the cascaded series of the filters in response to an input spike, which is appearing in the fire command. Maybe I better if I change to, oh, I cannot. Okay, so then each physical component of the seismic system, source, receiver, recording instrument, etc., can equivalent to a filter black box, because at the end, maybe theoretically we know what was emitted to the earth, but as at the moment is getting lots of different small changing. It's not 100% what we are what theoretically we've planned to emit. So if you can see the whole series, so we have the fire command, then we have a source signature, then we have a source coupling on land, Then we have the source array response on marine. Then we can do the source ghost. Then we are reaching the reflectivity, but of course, as we are going down and up, we have the absorption, then the interbed multiple, then water bottom multiple, then receiver ghost on marine, receiver array response on land, receiver coupling on land, hydrophone geophone response, and the recording instrument response. So all of these things together and during the processing, this is a black box, and this is what we would like to reduce with the deconvolution, because finally at the end of all of the exercise, what is really interesting for the interpreter is the reflectivity series, what we like to recover from the seismic data. So the deconvolution is finally doing that compress the seismic wavelet, so removing several filters statistically or deterministically. Then attenuate multiples. If we have multiples with very short reverberation, we can also attenuate with, and compensate for source and receiver effects. So what kind of multiples, what kind of deconvolution, what we are doing during the processing? We have the predictive deconvolution, which is statistical. So we are computing based on the input data, and the phase is not manipulated during this deconvolution, and the short period multiples are nicely attenuated with the predictive deconvolution. The second main type of deconvolution is the spike deconvolution, also statistical, so it's coming from the computed based on the input data. We have usually a minimum phase input and then zero phase the output, because also the spike deconvolution has a whitening effect to boost the higher frequencies and the lower frequencies. Then very nicely supporting the merged data sets with different sources, because also it's calculating the source different very nicely, mainly when we have we are using as a surface constant way. And then we have the third type of deconvolution, the source signature deconvolution. This is on marine, or when we are using air gun, because with the air gun we can record the signature of the air gun. And due to this is deterministic. So it's not coming from the data, it's coming from the recorded wavelet. We are calculating this based on the far field signature. Also now we are using near field signature to use it, and we have a zero phase output from this deconvolution. One short example for the deconvolution, you can see three stacks. On the left side, you can see land data without any deconvolution. What you can see that this is dominantly a low frequency, so low resolution picture, and we can see some short reverberation of the data. What is very hard to see, but if we are comparing with the middle one, which is a predictive or gap deconvolution, because we can see that slightly it's improved the resolution. Still the noise content is fine, it's more lower frequencies, and some event is disappearing, which is judged as a short period reverberation. And the right side, we can see the spike deconvolution. If you see in the shallow, you can very nicely see that the resolution increased a lot. But also with the resolution increasing, we are increasing the noise content, because in higher frequencies we have quite a lot of high energy, high frequency noise, and this was boosted more. And with the resolution increment, also this section is more noisy from the high frequency part. So these are the three different, so the two different deconvolution on land, and this is the effect of the deconvolution. Then most of the steps what we did up to now, it's happened in shot gathers or receiver gathers, so which is connected with the acquisition. But now we start to have to change to common midpoint gather, and I put here the definition of the common midpoint gather from the SCG Wikipedia site, because I think it's a quite nice definition. So what you can see here, that the seismic data acquisition with multifold coverage is done in shot receiver coordinates. And this is what you can see on the figure A. And then you can see how the shot point is emitting the waves, and then we are recording on the geophones. And you can see the first source and geophone or receiver side. In the middle, you have the midpoint, and this is the common midpoint. But that means for each shot gather, the midpoint, you have lots of shot gather. So when we are doing the resorting of the data, we are doing most of the steps from this point as a midpoint and offset coordinates. So the coordinate transformation can be achieved by the sorting the data in the CMP gathers, what you can see on the figure B. So we have lots of shot point and lots of receiver point, and the main things which is connecting them, that all of them, if we are halving the offset between the two, then we have the midpoint, and this is the common midpoint, where we are collecting all of the information, and we are collecting all of the data in one gather which is connected with that midpoint. So this is the common midpoint gather. And this is also many times in the you can hear as a common depth point gather, but I think the common midpoint is more appropriate, because yes, in horizontal isotropic layers, the depth point and the midpoint is falling together. But you will see later on during the migration that finally in a normal environment, the midpoint and the depth point is different. So this is why it's better. And in the next steps, I'm using just the common midpoint terminology. How does it look like in the real data, this resorting? So in the left side, you can see a marine boat. You have a shot, and you have several traces for each geophone. So this is the acquisition sorting. And you can see several shot records as the boat is going ahead and shooting more and more and more. Then, if you see here in the blue part, we are from the different shot point, we are picking up the same position, which is the same midpoint. And then we are turning this as a common midpoint gather. And this different records is building up the common midpoint with different offsets. And this is how it's appearing at the end, or picture that the CMP gathers as common midpoint gathers are appearing on the right side. And this the upper side with this orange lines, I just representing the lots of shot and receiver point, which is connected at the end for the same midpoint in the middle. So this is when we are changing the geometry, and it's creating for us a different seismic processing sorting. Then in land, we would like to apply static correction, of course, because we have the topography effect. And this is usually creating lots of trouble. So we would like to remove really on land the near surface. And we would like to remove these different time delays, which is appearing mainly on the near surface due to variable receiver and source elevation. So we would like to put everything on a common datum. We would like to remove the near surface weather layer. Can be changed horizontally, have different thicknesses. We can have caves under the surface, and this is creating some time delay. So all of this delay, we would like to convert it to a layer which is already well consolidated and very nicely homogeneous. And also we can have other near surface layer velocities. So we are correcting everything from the surface to the base of weathering status, weathering datum, to really to get back properly and remove all of this effect. This is happening in time, and also this has advantage and also a disadvantage. So the advantage, we are removing this unwanted effect, is perfect, but we start to change the ray path of the events. So if you see, you have the surface position of the source and the receiver on the surface with S and R, and in the subsurface the pseudo position. And the issue is that we have the nominal true ray path, which is describing this near surface, but this true ray path we are changing to a pseudo ray path, which is in time could be kind of solution, and I will show you a nice example about it. But in depth, this can generate issue, because then from that moment our ray path is not the correct ray path. So many times when we are doing time migration, this is a good solution, but when we are changing to depth migration, we have to go back more close to the surface and write down more properly the near surface with velocities. So example for the static. On the right side, you can see a small map. In the middle, you have the red line with an arrow, and this is how the red line is going through on different areas, which is starting on the south side with sand dunes, which is a quite complex static issue. Then we are reaching the transition zone, which is a flattish gravel, and also we are going the mountainous part, which could be very high elevation variation. And you can see that finally this line is going through several valleys and also tops. On the left side, you can see the stack section for this line, and above it you can see how the elevation is changing. So really we have a big elevation change during this line. And we can see on the right side that we are in the mountainous part, and we have less elevation variation. We are reaching the gravel, and then at the end we are reaching the sand dune part, which is a very fast, small variation of the elevation. But as the sand dune has a different content and different slowness for each part, it can be really destroy the picture. And this is what we can see. So if we are going now to the section, on the right side, you can see that even in the mountainous part is quite nice, the signal to noise ratio. We can see quite nicely described reflection, but we can also recognize that this has some ondulation, and this weaving is connected with the weaving of the elevation. So in this part, we have a good energy transmission because we have a good quality of data. The near surface is not that complex, but still it's creating some issue, which is not totally good. But in the sand dune area, the whole picture is totally useless because the events are not focused and also not nicely aligned. And this is with the field static, which is a kind of brute static and a very simplistic model with only one velocity in this area. So usually we have to start to work on it and build up different static model. And after lots of work in the final static, we can get the picture on the right side. So what we can observe on the right side of the mountainous part, we already removed the waving, and everything is quite nice, flattish with the proper near surface velocity model. And which is very good on the left side. Also, we started to get coherency, and we have a good, much better focused signal at the end. Still, what we are seeing is the energy absorption, which is below the sand dunes, are way higher than below the mountainous part. And also we can see that finally on the left side we have more low frequencies, because unfortunately the higher frequencies are destroyed very fast in the sand dune area. But the static solution already provided us a nice followable events, and this is already, it's a good step, first step for the interpretation, when we were able to recover all of the topography and near surface problem, and then we are generating a nice input for the interpretation. So this is the static, and this is the importance of the static. So some area, it's not that big issue. In sand dunes, yes, it's a big issue to recover it properly. Then we talk about the static correction. Static correction means that the whole trace is moving up and down with different value. Now we are going to the dynamic correction when the trace is moving so we are applying dynamic correction, so not one value for the whole trace. Why we need this? because it's again on the upper part you can see different shot and receiver position. We have the as we used before, the isotropic 2 layers model with 2 different velocity. We have a reflector where we are getting back the reflections, and then we have different offsets between the source and the receiver, the x2, x3, x1, x2, x3. And then what you can see below, that the measurement, how this is appearing on the gathers. We have the top of the hyperbolic curve, so we can connect all of the, if one event we would like to connect, we can connect with the hyperbolic curve. You can see the equation for one layer, that the time of the apex, so the peak of this curve in different offset is depends on the zero offset time plus the offset divided by the velocity square. And then in this case, the v velocity, what we are using in the equation, is the same as the v1 velocity. So this is very easy to tell in one layer and in time. What you have to know also, this is an assumption for the NMO compensation. At the moment is working based on that one. This is what we call the second order velocity. We have a much longer equation for the proper velocity description. Just I did not include here because then we can go also a different direction. So at the moment, most of the time when we are talking about velocities, we are doing this conversion for the velocities. And this is for one layer, and now I am changing for several layers. So if we have n layer, and you can see again, I'm using a simple model with n layers, also horizontal isotropic layers with different velocities. When we are calculating for n layers the same equation, these are not true geological velocities. And the question is always, what is v? And in time, what you have to see that the actual curve ray path, because the ray path start to curving as we are going through different velocities, always replaced by a straight ray path. And this is how the RMS velocity is building up. And when you have multiple layers environment, during the RMS velocity is always, this is an assumption that on the given point where we are connecting with this velocity is always the multiple layers replaced by a single layer. And this is where the time processing is, or time imaging is very robust. But also this is the issue that finally we are not writing down the proper ray path. But many cases this is more than enough as a good assumption to do this part. I will come back to this during the depth migration, because then we start to use a different velocity for this. So how does it look like, the dynamic correction? So you can see on the left side the CMP gather. So we sorted the data from acquisition to processing domain. And these are without a dynamic correction. Already the noise attenuation happened on this CMP gathers. We can see very nicely we have the reflectivity on the gathers. And what we would like to apply the NMO based on the equation what I just described before. And when we are applying the NMO, then the layers for the same, so the signal for the same event very nicely aligning. And what we can see that that this is why we have this red lines, that for each refraction, which is at the moment without dynamic correction, it's hyperbolic behavior. Now we have absolute flattish and nicely aligning everything. What we can see as we are going in further and further in the offsets, then the data started to be more stretched, and this is why it's dynamic correction, because each data is moving as we are going with the offset more and more to get the same alignment. And at the end, what we are reaching also, that we are stretching more the data. And the thing is that as we are interested mainly the clear data and also the high resolution, we have to do something with this stretch signal. And also we have several linear noise which is still remaining in the data and also stretch more. So this is the step when we are applying the mute, and the mute is trying to cut off all of the stretch signal and preserve just the data which has the same resolution. So this is the data after an MO correction or dynamic correction without mute. And this is how we are generating with the mute the clean signal for the next steps. So then we are applying the mute and we cut off all of the unnecessary noise from these gathers. Yeah, so when we did this, then we are reaching the next step, which is the multiple attenuation, because when you see this data, sometimes you can recognize that so the signal is nicely aligned, but for example in the third CMP we have some still curving part, and the question is why do we have this issue? Because if everything is corrected properly, then we should have a flattish information for different offsets, and this is where the multiple attenuation is playing a role, and then we have to perform these steps. So multiples, what you can see here, several on the higher picture, we have several ray path, and we have in red the primary ray path. So if you see what is appearing, we have a shot point on the left side, we have a receiver point on the right side, and then it's going down the ray path to the deepest boundary and then bouncing back to the receiver. This is what we call in the primary, but unfortunately with the same time we have several arrival from different events. For example, the blue one is going down for the first boundary, then it's bouncing back, then it's generating another virtual shot point and turning back and going to the second layer, then again is bouncing back up to the first layer, then going down the third layer is bouncing back to the geophone. Then we have the peg-leg type of multiple, which is starting from the second layer and start to bounce in different parts. So what is the difference between the primary and multiple? So by definition, the multiple is energy which has more than one reflection and its travel path. So as you see in the red has only one reflection, one travel path. In the multiples has several reflection and it's arriving different time than the primary. General properties of the multiple usually has lower velocity because it's not going that deep. So this is why it's appearing as a different velocity because it's not going deep and the velocity increases with the depth. Then has a higher amplitude because we have less geometric spreading, so very strong energy is preserved due to the less spherical divergence. It could be periodic, depends how many times it's bouncing, and this is repeated cycles with the horizontal layers. And what we are doing many times today that we are trying to predict them from the primaries, and then this is how we are using the multiple model to attenuate the multiples. So I'm just showing two examples because this topic is already very big, but I would like to just show two examples. Left side, you can see two CMP gathers after dynamic correction and mute before multiple attenuation. And the right side, you can see the same gathers, but after multiple attenuation. So if you start to see the left side, the gathers, you can see that, as we discussed before, the primary should align as a flat event. So you are getting this through the offset domain that quite nicely flattening up everything. But both above this event and both below, you can see lots of curving event, which is showing that this energy most likely is coming from the multiples and they are not aligning properly. So somehow it's better if we start to remove now and then we can do something with it. This is a quite relatively easy multiple because we have the difference between the the primary and the multiple as velocity difference, and then we can start to convert different domains, and then we can start to attenuate in this domain the primary and the multiple and preserve the primary. So on the right side, this is what you can see, that after the multiple attenuation, very nicely you can start to recognize the flattish events. And mainly in the deep, around 3000 milliseconds, you start to recognize that not the main event is really flattish and not the multiple, although the multiple energy is higher, but after the multiple attenuation, you start to reveal the primary events. So this is our goal at the end, to remove the primaries as to remove the multiples as a coherent noise and increase the primaries signal to noise ratio. Also, there are several issues with the multiples. So the multiples are interfere with the primaries, and also for the interpreter can be give a false picture, and then they can be interpreted as a primaries, as they are also very high energies. Of course, multiples are affect the imaging processes, because the imaging always assuming a multiple free data, and then it start to spread the multiples for different areas. And you can imagine that the AVO calculation, which is the amplitude versus offset, how the amplitude is changing with the offset. This can be affected also because, as you see on the first picture, all of this curving energy is really hiding and overwriting the real energy calculation from the primaries. So this is why we are targeting and working a lot to try to eliminate the multiples. Also, we have here a very big issue as they are higher energy, we have to put lots of effort to not to attack the primaries and preserve them as much as possible. I would like to show you another picture, which is really showing that how the multiple issue can be destroying the image. In the left side, you can see the stack before the multiple attenuation. We have huge amount of events, huge amount of energy on this part. And the question is that the interpreter, that in this case, how we can really follow the interpretation, which event is true, which is not. And when we are removing all of the energy from the primaries, you can get the middle picture. This is the stack after the multiple attenuation. And really what you can recognize here, that huge amount of energy removed, and different events which is connected with the multiples also removed. So if you compare the left and the middle picture, really you can see that lots of event which is appearing on the stack before the multiple attenuation almost completely disappeared, and it's enhanced the primary after the multiple attenuation. On the right side, again, you can see the difference, and really you can see that what is the energy, what we have to remove to reveal the middle picture. And again, here, one of the big questions, and this is why we have to do several iterations for the multiple attenuation too, to be sure that with this big multiple energy removal, we are not affecting the final primary image, and we are not touching them. Yeah, so this is about the multiple. And then the next step is the stack. And what you can see here, it's again a very simplistic two layers model. Rho 1 density, V1 velocity, rho 2 velocity, V2 velocity, with the reflector, the shot points are there, and the receiver points are there. And of course, in the middle, we have the common midpoint. And this is one of the big reasons also why we are doing the common midpoint sorting, because you can see the different ray path, the red, the green, and the blue one, which is connected with the same midpoint. And then what we are doing, we are adding them together after all of the corrections, so static, dynamic correction, noise attenuation, multiple attenuation, deconvolution. And what we reach with that, all of this pre-processing step, that we have the signal which is nicely aligning for each offset. This is also why we generated earlier the dynamic correction. And all of the random noise is nicely attenuated. And in the bottom, you can see the dynamic. So you can see the multiple present because you can see that the same higher energy but in different time due to we have the different offsets. So again, the blue is the near offset, the green is the medium offset, and the red ray path is the far offset. And what we can see that when we are adding together all of these things in connection with the signal, we have a constructive interference, so we are increasing the signal on this part. In the random noise, definitely we are destroying the noise, and we increase the signal to noise. And also in the multiples, where we have bigger velocity differences, and maybe we have sometimes remnant multiple presence, we have a destructive interference because they are not aligned, and nicely also we started to attenuate the remnant multiple content. So with the stack, this is the final effect of the stacks, that the aligned signal is enhanced, and all of the other things, which is the noise category at the end, it's not aligned, is quite nicely started to decrease, and we created a signal to noise improved gathers on that common midpoint. So what's happening here, you can see a series of common midpoint. After noise attenuation, after static correction, after NMO correction, everything, after mute, and then we are adding together each common midpoint gather, and we are representing them in one trace. And when we are putting together all of the trace, this is the way how at the end we are building up the stack section. And this is how I showed you previously all of the stack. This is it's happened in all of the previous case of the stacks. Then the final step, what we are doing is migration. So the question is, why we need migration? We need migration because we have the seismic data records. This is our field acquisition scheme. And then we are measuring mainly the travel. We are measuring the travel time of the reflectors and not their spatial positions. So if you see in the left side, this small picture, we have a source, a receiver, common midpoint in the middle, and we have an isotropic homogeneous environment where the ray path is going. In this case, the spatial position and the travel time is really writing on the same point. But even if we start to do a small, so we are doing the exercise on a dipping event, and also if the layers start to be inhomogeneous and non-horizontally layered, then the reflectors are not in their true location in the stack data. And this is what you can see on the right side. So you can see the same midpoint, and all of the source and receiver is connected with the same common midpoint. But if we going back to the Snell law, and we are thinking that the incident angle and the reflection angle should be the same, and it's vertical to the axis vertical to the layer, then we start to recognize that finally the depth position of the ray path is very different compared with the common midpoint. And this is when we are applying migration, we are moving everywhere to the right position the event. So very small, so we need the migration. So very small sketch about the same thing. So in the left side, you can see the accuracy of the reflection point. This is the same exercise as I just explained in the previous page. We have the common midpoint for different source and receiver, but finally is describing a different subsurface position. And we are seeing this in a midpoint, several traces, apparent reflector position before migration. This is represented with a red dashed line. And then with the migration, we are moving to the actual reflector position, this event. And this is when we can see really in position the reflectors where we are getting from the signal. Also, another symptoms what we can so many times, if we have variation, so it's not horizontally layered flat environment what we end in the deep surface, but we have some specific position, then in this position we can generate diffractions, And then this is what we can measure as a diffraction, which has a very different apparent velocity than the primaries. So also the migration task to collapse this. And this is what I show you in the next picture. So I would like to show you some two basic subsurface event. One on the left side is an anticline model. The right side is a syncline model. We have two different velocities with one layer, and the anticline is syncline in the middle of the thing. So first, let's see the anticline model. When we are doing a zero offset acquisition, so in the same position we have a source and the receiver, we can see the rate of how it's going down. So we have one arrival from just below because we have the same position, the source and the receiver, but also we have an arrival from the anticline structure. And as we are going closer and closer, you see that one arrival is always in the same time, which is representing the flattish part, but the other arrival has a different ray path. Longer and shorter depends where you are. Shorter when you are top of the structure, longer when you are far from the structure. And this is the picture how it's appearing on your seismic data. So what you can see that the anticlines usually is broadened during the seismic data acquisition and before migration. And this is how you can identify them. The flattish part is the same because it's not complex, but the anticline already spreaded and broadening quite a lot. And when we are applying migration, then we are getting back the anticline event in the proper position. Yeah, the same things with the syncline. Here you can see the 1, 2, 3 as three different parts of the anticline, and we will see how does it look like this on the seismic section without migration. So what you can see here, the ray path, the vertical part is the same, but then in the middle, in the syncline part, you have a buried focus, and this focus also is generating different ray path. When we are seeing the unmigrated time section on stack, you can see this bow tie effect. And you can see that what it was signed with 1, 2, 3 numbers, you can see that how it's appearing the different travel time in the bow tie part. And then, of course, when we are doing migration, this bow tie is collapsing to the proper place. So this is about the theory. And let's see an example. So what you can see here, it's a non-migrated section. In the shallow part is very flattish, so I am not expecting here too much change. But as we are going deeper and deeper, we start to see this bow tie and also the broadening of the anticline. So we have here the anticline, syncline next to each other. So when we are doing the migration, then everything is collapsing back to the normal position, and this is how does it look like the real image, which is after migration is built up. So on the upper right section, you can see the non-migrated section, and you can compare that how the events are collapsing properly to the right spatial position, and what was the appearance, all of this diffraction and broadening what we had before on the unmigrated stack. So it's again, this is the input with lots of things in the deep, and this is the output, and nicely collapsed everything to the right location, and this is the right input as this is the subsurface real image in the deep. Then I would like to just mention the 2D versus 3D migration, because also it can cause some issues. So the 2D lines are measured under one line, and this is like you are slicing a cake. So if we have a simple geology, it's okay, it's fine, because you are getting from the same locations the arrivals. But in 3D, you can have side arrivals. So it's many times on the 2D migration, you cannot correctly model see everything, because you can have side arrivals, and this is what you can see in the below pictures. So in the upper pictures, you can see the 2D lines when you have dipping layers in the direction of the 2D lines, but the lower picture is showing when you have a 2D assumption, but unfortunately, due to the 3D structure, you have lots of side arrivals, and then it's impossible to collapse properly during the migration to the right place, what we are seeing. And on that way, the 2D line cannot show the right picture. So how does it look? And then you need, of course, the 3D migration for solving that images. And this is how it looks like on real data. So this is a 2D migration, and you can see in the deep what is the position of the deep structure based on the 2D migration. Also, you can see that we have flattish events. So what we can expect that where we have simple geology, the events are not changing. But as we are going deeper with complex geology, if we have a 3D migration, that 3D migration can be place or move the things to the right location. So this is the 3D migration in the same area, and this is the 2D migration. So 2D and 3D. We can see that lots of things what is appearing in the 2D, and it's not in the right location in the deep. In the 3D is going to the right location, and at the end you will have the proper input for interpretation. Again, what you see in the shallow, the flattish events or the non-complex geology is staying in the same location because the 2D assumption is fine, but everything which is deeper and has a bit more complex geology, the 3D will give you the proper image. So then I'm changing domain. So we have the time versus depth migration, because everything you have to remember when we discuss that the RMS velocity is an assumption of the velocity, but not the proper one. For that reason, we are using now the depth migration where your input is the interval velocity. So for each layer, you don't have a replacement velocity, but each layer is going to the migration with the own interval velocity information. So a comparison between time and depth migration. In time migration, velocities are less geologic and have a low spatial resolution. Depth migration velocities are more geologic with higher spatial resolution. In time migration, the lateral velocity variations produce mismatching. So always when you have a bigger lateral velocity variation, the time image won't give you the proper result. I will show you in an example in the next step. The accuracy in the depth migration is giving us a better focusing and more stable phase of the data, and also the location is better described. And then the time migration is strictly valid only for vertically varying velocity. It does not account for ray bending at interfaces. This is a big limitation of the time migration, but also the time migration is quite robust application. Many times we like to run always time migration and then compare with the depth migration, where we can really see what is the improvement in the pre-stack depth migration. Also, we can be sure that that if the depth migration for some reason is worse than time, then maybe we did some mistake. And then, of course, the depth migration accounts for ray bending at interfaces, but requires an accurate velocity model. So this is very important, that how we can build up the accurate velocity model. So we have two examples here with the salt model in the middle. On the upper image, we have the 3D pre-stack time migration, and we can see that the event which is finally at the bottom of the salt has a very poor focusing, is not moving to the right location, and it's not helping the interpreter. Compare with the 3D pre-stack depth migration, where the bottom of the salt, you can really see it's described on the right position, and it's no problem if we have a big velocity, lateral velocity contrast, because between the sediments and the salt, many times we have very big velocity contrast, and this can destroy the time image, but in depth migration we can reveal better. So what we can tell about the pre-stack time migration, that we have a vertical distortion, we have a poor focusing in case of big lateral velocity contrast. The migrated time is not the same as the vertical time because the event did not move to the right position, so energy still it's a wrong position. And the lateral contrast, it could be described only in pre-stack depth migration. As I mentioned earlier, we have to build up to get the proper depth migration image. We have to build up a proper velocity, subsurface velocity in depth, and this is what is the main part of the pre-stack depth migration. And you can see in the upper right schematic scheme of the velocity model building or the depth migration, how we are doing. So we have the time velocity model, which is very smooth. Then we have the gathers in time, and we build up the initial model from the time migration velocity model. Then we are filling in iterative loops where we are migrating this data, QCing if everything is good. Then we are doing a residual velocity analysis. Then we are updating with this result the model. Then we are running a tomography to further update them. And then we are running migration. And we are doing this until the main QC is we are reaching the flatness of the gathers. So in the below picture, you can see the free gathers before tomography and the same free gathers after tomography with the right velocity. So what you can identify that the events are not flat with the initial model, and also they are in wrong depth because now everything is happening in depth domain. With the final velocity, with after, I don't know, 3 to 6 iteration, we are getting the events are flat. So we are getting for each common image gather, because now these are the proper domain for them. Then we are getting flat gathers, and also we are getting the right depth because we are closer and closer the event proper depth. So this is, as we are reaching the best flatness, we are finalizing the velocity of the iteration, and then we are running the final depth migration with the right tools. Yes, so the PSDM, it's a model-based seismic imaging methodology that works well for complex geological structures. If the structure is not geological or the velocity is not giving us additional challenges, then the time image is perfect. And also what we have to know that the PSTM comparison with the PSTM is more expensive and time consuming. So we have to build up a proper image, and this is the main focus of this part of the processing. But at the end, we can more precisely describe the subsurface structures, and we can give the input to the interpreters to describe properly the reservoirs. Yeah, this is the tomography result, what you can see. So on the left side, you can see the initial velocity model, very smooth, is coming from the pre-stack time migration, not too much details. And as you see the final model from the updated, for the tomography iterative updates, we can see that we have way more details in the velocity model and much better describing in the subsurface, as also its interval velocity, and then we are ready to run the final migration. Here we have one more selection, so we build up a very nice model, very nicely fitting the flatness, but still the issue is what we have to put always in our mind, that the depth velocity is not unique, because we can get the same flatness on different depth, and for that reason we have an uncertainty in the depth velocity model. So we have to reduce this uncertainty. As you see on the left side, you can see a section with the interval velocity model, which is really complex. You can have velocity inversion, you can have higher velocities, lower velocities on the top of each other, and when we try to describe this, we can reach different result. But for that reason, we are many times we are using a priori information, and we have the option to constrain the calculated velocity model. So we can use geological mugs, geological cross sections to create constraint. Well formation tops is very important to see in the well tops what is the level what we reached. We can use the sonic interval velocities to compare with the tomography velocities and try to stretch to the sonic the tomography result. Also, as I described, in time, we are using static to remove the near surface anomalies, but also we are changing the ray path with the steps. So nowadays, we are including the near surface velocities from refraction statics to the velocity model to properly create an initial model for the depth migration and the tomography update. And also, we can have location of pitfalls such as pull-up on time section. So we can geologically start to manipulate the velocities to better describe the velocity field. So this is one example for submarine canyons. So what you can see here in the upper part, the PSTM velocity arrived from the PSTM. This is the initial velocity. Is very, very smooth, is very nice, gentle. But also what you can start to see that in the deeper structure is affected the near surface variation, not properly described near surface variation, and started to wave the seismic based on the initial velocity, because the shallow canyons did not describe well in the velocity model. And after all of the update and building all of the a priori information to the velocity model, you can see like in the middle we have the channels handled differently, and each channel has a different velocity compared with the initial PSDM velocity. You can start to see that the event started to be flat, and all of the waving which is affected by the shallow variation now is totally flat. And this is also showing that the structure described properly, and this could be the proper input of the interpretation, because it's not creating fair structures in the upper picture. So this is the importance that at the end we have one part of the velocity which is fully data driven. This is the tomography, and then after or even during the tomography we can start to manipulate the input velocity field with different geological information and try to build up a better input for the next tomography update. And then at the end we can really describe better the subsurface. So we reached that point that we have nicely processed data, we have nice velocities. So now we just have to run the migration. And in depth, I would like you to, sorry?
Yeah, this is Laura. Just a short reminder that we reached 90 minutes for our session. So
okay.
Yeah, we should.
It will be 3 more slides. So this is really the last. Yes, thank you, Laura.
This is a good match. Thank you.
Yeah. So we have depth imaging tools in depth migration, what we have to use, and we have to select the right tool. We have two main things. We have several other methodology. I just describing the two main things what we are using nowadays. We have the ray-based method, which is the Kirchhoff migration. We have which is good, is focusing on diffractions, is very fast, very cheap, consistent with the tomography, amplitude preserved, but there is a main limitation, the ray tracing in complex mode, and the multipathing is not possible with this methodology. And we have our ultimate tool, the wave field exploration based method, which called reverse time migration. And there is no limitation complexity of the models, very, very good handling of the multipathing, turning waves, prism waves, very well handled. But the issue is it's very expensive. The cost is exponential with the frequencies, with the resolution. And also we can generate angle gathers, but it's 10 times the cost than if we just generating stacks. So it's really, really, it's an expensive thing, but there are some locations where we have to apply. And this is what I would like to show as a difference between the two things as a last part of my presentation. First, I would like to show you on the synthetic data. This is the EIG SEG salt model. You can see the blue is the sediment around the salt. And in the middle, you have the salt with the salt velocity. The color is representing, of course, the velocity. Reddish is high, the blue is much lower. So how is behaving the two methodology on this model? Left side, you can see the RTM results. So it's the same velocity model, just the imaging is different. You have the reverse time migration on the right side, and more or less you are getting the proper image. And as you see here, no limitation in complexity of the models, handling the different waves, and improving the subsurface image, which is very important many times, that how does it look like below the salt, the image. But we have loss of resolution because we have a cost issue. So really we can run higher resolution when it's justified. And also the phase is sometimes questionable. Kirchhoff migration is very fast and cheap. Amplitude preserved, the improved subsurface imaging is a wrong sentence here. It's not true. So it's a destroyed subsurface imaging. Ray tracing in a complex mode and multipathing is not there. And also, yeah, the subsurface image is poor. So sorry, I have to delete one line from here. And this is what I would like to show here. In yellow, you can see that we have a prism wave in that small structure, and the Kirchhoff is not able to handle. Also, it's not able to handle the bottom of the salt, and the subsalt image is totally destroyed, so you cannot see anything for it. And the last two examples, what I would like to show here is just real data Kirchhoff and RTM result. So what you can see here in green, we have a very good resolution on the sediments. We have a poor definition with the red of the base salt, so it's really not aligning the things. And the migration smiles as the operation noise in the blue areas, we can see quite as dominant part. The same picture with the reverse time migration. We can see, as we discussed, that the low resolution of the sediments are there because it's very costly, the higher resolution, but we have a very good definition of the base salt and the shallow subsalt sections. So this is what you can see on the red circle, and the operator noise is very limited. So if we have very complex geology, it's worth to do the investment and run with a more complex imaging algorithm, because then this is which is really giving you the two pictures. So Kirchhoff has the own limitation and advantage, but really in structurally complex areas, we have to do the reverse time migration. And that was my last slide. So thank you very much for your attention. And sorry, Laura, that I'm going through.
No, thank you so much, József. This is the kind of bootcamp that honestly I would review. I would go and I will listen again this session on demand. József, I encourage our participants to drop their questions in the chat box. And I will start with the first one, which was dropped, I have to say, pretty at the beginning of the session. So maybe you already answered, but let's take this question. So Alia asked us if you could explain what does velocity on geological model means. Does it means velocity of P waves that could determine the specific layers? And
yeah, I think I already answered you. I hope I answered already during the presentation for this part. I don't know if need any further clarification because I explained a lot with the velocities and also with the migration velocities. So I don't know if it's
this answer in one more minute, just to have it on record that. So just a clarification. When I remember.
Yes. So the main thing is that in time velocity we have a smooth layer, and for the given layer is more RMS value, but in depth with the interval velocity really is describing properly the geological layers, and this is where really you can connect the geological layers with the given velocity. What is measured with the flatness of the geders and also what is measured with the wells, and then you can make connection between the two things. Yeah.
Thank you. Okay,
Yeah,
thank you so much.
which processing
Another-
changes likely affect onshore 2D data in Netherlands?
Okay,
Yeah, I was looking for some section. Most likely you don't have static challenge because the static in Netherlands is, so the area is very flattish. I was working big data there, and yeah, the static was not really issue. More that how the velocities are described. I think also the noise attenuation is working quite well. So you have a nice preserved amplitude data, and also this is a good input for your inversion. So maybe the imaging, when you start to have very complex things, then it could be an issue. But also, yeah, it's moderate the challenges. So I cannot tell that it's very difficult from processing side the data in Netherlands. Yeah.
Another question from Gordon: if the amplitudes are not preserved in the processing, how might this impact the seismic inversion?
Then it's so I would suggest to go back and to do again the processing with preserved amplitude, because for the seismic inversion is necessary that you need the preserved amplitude. So in some areas where the signal to noise ratio is very poor, we have to forget this method because we're just going for the structural picture. But in connection with the amplitude, and if you would like to run inversion, then you need the preserved amplitude. And this is why we are putting lots of effort to with the noise attenuation, with the multiple attenuation, to preserve really the primaries, because then this can lead also for further reservoir characterization methodologies.
Thank you very much, József. I do not see any other questions. Let's wait half a minute. Meanwhile, I can remind our participants that our next session is going to happen tomorrow. And now I'm sharing my screen just for you to see who will be our upcoming speakers. So Mateus Zareba from Halliburton, he will introduce us tomorrow. Machine learning methods is the first bootcamp on this topic. There will be another one later in the month. So please join us tomorrow, 10th of October, same hour as today. And I will stop sharing my screen with this. No other questions. So at this moment in time, I will... no, we have 2 more questions. Sorry. What is the difference between 3D migration and the processing of 3D cubes? This is a question from Bara.
This is the 3D processing is happening on 3D gathers, so also the short gathers are 3D, the CMPs are 3D, so everything is adapted. So in the ancient time, the 3D were handled as a 2D things, and we sliced up the data to virtual 2D parts, and then we are doing the 2D processing and imaging based on that assumption. Nowadays, we are using always, if we have 3D, we are using always 3D gathers and 3D imaging to get the proper subsurface image, because also all of the noise, all of the multiple, all of the signal created in the 3D way. So if we are doing 3D, we have to do everything in 3D from pre-processing up to image, final image. Yeah.
Okay. And the last question that we got, how much of the processing is completed with artificial intelligence?
Not too much, unfortunately. So I'm really hoping that somebody is creating some good benefit. We have several trials for the artificial intelligence implementation, but still we are not fully there. So the noise attenuation, there were some trials. Self-organized map, also there are some trial. Velocity analyze, there are some trial, but still not fully in production. Yeah.
And the very last question, and this in relationship with the previous one you answered from Bara. So the one related to the difference between 3D migration and processing of 3D cubes. The question is, will the processing steps still be the same?
Yes, it's just the domain. As I told, the domain 2D or 3D, this is which is the different. So we are doing the same things. 3D, it's a bit more complex, the part, but the processing flow, what I described at the very beginning, are the same. Yeah, so it's no change. Yeah.
Thank you so much, József. Thank you one more time. I know
Thank
how
you.
busy you are. I know how many things you have on your plate. So thank you for your time. Thank you for accepting our invitation. See you tomorrow with a new bootcamp. And with this, have a nice evening. And thank you very much to the ones who are live with us. Thank you.
And I don't know if somebody has any question about the presentation in the future. How are they?
We are going to kindly ask you, but we will take this offline to share with us the slides that you are allowed to share. And we are going to make sure that they reach our participants.
Okay.
Well, I have a question,
in this
please.
format. Yes.
Yes, I have a question about the recording. Where can I find them?
The recordings are available on the Discord channel. And few hours or in the next day after the bootcamp, each session becomes available for the participants. Make sure you are registered on the Discord channel.
Yes, okay. Thank you so much.
Pleasure.
Thank you.
Thank you, everyone.